Let's have a look at practice question set number 11, all 10 of those questions. We start off with question number 1. It says, the following diagram shows 2-point sources and selected field lines. The solid field lines result from determining the direction of the net electric force acting on a test particle placed at a point along the line. In other words, they are the electric field lines, right? The electric field lines as we know them. It says the direction of the net electric force acting on a charge placed at a point on the line. What type of charge would it be placed at a point along the line? These solid field lines result from determining the direction of the electric force acting on a test charge placed at a point along the line. Be a positive charge, right? Because that's how we define the direction of the field. If we put a positive charge right there, it's going to move along that field line. It always experiences a force in the direction of the field, which is away from the positive and toward the negative. Now, the dashed field lines represent or result from connecting those points on a plane that have the same electric potential when a test charge is placed at that point. Potential, remember we talked about potential difference briefly. Potential difference is related to the energy of the particles. Okay, these seem confusing though. These dotted lines seem confusing. But I'll tell you what, go to do this question. It's not going to mess us up that much, right? Okay, we can still answer this question, even if we're at this point still a little bit confused about potential and potential difference, which, by the way, does become a little bit clearer later today. Number 1, the field lines represented by the solid lines are classified as, well, they're vectors, right? Because they have direction associated with them. There's arrows on them, right? The field lines represented by the dashed lines are classified as, well, they don't have arrows on them, so they must be scalars. Done. That's all we need to know about that, right? So don't get bothered by a statement in the second part that seems a little bit confusing. It doesn't really matter that it's a little bit confusing. Next question. Numeric response number 1, the electric field strength at a distance 4 centimeters from this charge is going to be what? This is a pretty straightforward question. All we do is say, we got a producer here, a non-uniform field producer. So as opposed to E is equal to delta V over delta D, we're going to say E is equal to KQ over R squared, which is 8.99 times 10 to the 9 times 1.2 times 10 to the negative 5. Divided by 0.04, and then we're going to square that and see what we get here. 8.99 times 10 to the 9 times 1.2 times 10 to the 5, 10 to the negative 5. And we're going to divide that by 0.04 squared. And that gives us 6.74 times 10 to the 7. 6.74 times 10 to the 7. That would be newtons per coulomb. But what's the other set of units that I could have used for that? What is it? Yeah, volts per meter. Yeah, volts per meter. Now, how are we going to record that? A, B, C, D. A, B, C, D. What's our answer there? Zane, what's our answer for that? 6, 7, 4, 7. Good. 6, 7, 4, 7. Now, if this was a B times 10 to the W question, which sometimes we see that, wanting the value of B, then we'd express it as 6.74. Okay? It's not what this is, and they tend to be, on the exams now, going towards the ABCD format as opposed to the B times 10 to the W, but we want to be ready for both, just in case. All right, bumper cars operating on electricity. The more the accelerator is pressed, the more current flows in the system, thus the faster the car travels. Car X and car Y are going to collide head on. Constant velocity. This looks like a collision question, right? PI equals PF. In fact, we could do that. It just wouldn't help us with the electric field between the top and the bottom of the grids. What kind of electric field do we have here? Is it uniform or non-uniform? Uniform. So we're going to use that uniform producer equation. E is equal to delta V over delta D. Pretty straightforward. Delta V here is 120, and delta D here is 4, so that gives me 30. We could say volts per meter. They say newtons per coulomb. Which way is it, though? Up or down? Field lines always point away from the, yeah, and toward the negative, right. So we got 30 volts per meter or 30 newtons per coulomb, whatever you want to call it, and that would be downwards. Now, oh, this just looks like a variable value changing thing, hey? You got a pair of parallel plates that are a pair of parallel plates that are separated by a distance of 1 centimeter. We probably want to draw attention to that. Connected to a 12-volt battery. The magnitude of the field is E1. Second pair of plates, different distance, different potential difference. All right, so we don't actually have to use variable value changing for this. We can, but what we could do is find the value of the electric field using delta V over delta D. Find the value of the electric field here using delta V over delta D, and then we could just divide them, right? That would work. Okay? I think, for me, I think I want to use the variable value changing. I think I want to say my original field is delta V over delta D. My new field is what? Delta V is half of what it was. It's 6 instead of 12. And the distance is 3 instead of 1. So we're going to say a half divided by 3 is 1/6 delta V over delta D. And delta V over delta D is my original. So we're going to say it's 1/6 of my original field, which means the answer is D. How many people got that one? Okay, how many people did it my way using variable value changing? Just a couple people? Okay, and so the rest of you calculated the fields and then divided them? Okay, there's value in that too. Just understand that if you're not given the numbers, then you can't do it that way, right? But there's value in that because what you did actually, one little thing that you did is an important thing to recognize in a number of questions that we see in Physics 30, and that is the comparison. Okay, if I want to compare E2 to E1, there's one word that I want to think of when I hear that word compare. Okay, we talk about, see, a force versus time graph, we always want to right away go to area equals impulse, right? Okay, a few things like that. When I see the word compare or something that's like compare, this is what I'm doing right here. One word that I want to think of, divide. Okay, I see compare, I want to divide. Okay, if I want to compare my age to your age, okay, then we would divide. Okay, you guys are 18. Okay, I'm 36. So we compare my age to your age. Maddie, what are you laughing at? My age to your age, we divide 36 by 18 and we get 2, right? Sadly, the ratio is closer to 3 than it is to 2, but nevertheless, as an exercise, we'll pretend that it's 36 divided by 18, which is 2. So we would say the age of the teacher would be 2 times the age of the student. Okay? Compare, divide. Compare, divide. Or if you want to find a ratio, we'll do that as well. Oh, here's a good one. The charge at a point A is Q, at point B is negative 16Q. On the line joining the two charges, where's the field going to be 0 at? Huh. Interesting. Interesting. Here's what I want to do for this one. I want to, at each of these points, draw the field lines, because I'm going to be able to eliminate a couple of these things, I think, right away. The field, let's call A blue, and B is going to be green, so we can kind of color code this, okay? The field caused by A here is this way. The field caused by B is this way. Now, we don't know their values, so I don't know if they're equal to each other yet, but we know that they're opposite direction. What about number 2? Away from the positive toward the negative. Well, that can't be, right? We can't make a net electric field of 0 when they're going in the same direction. We're going to find the same situation in number 3. Away from the positive and toward the negative. That's not going to work either. Here we go away from the positive, and we go toward the negative. Okay, which is it? Is it 1 or is it 4? Good question here. Is it 1 or is it 4? It's not 2 or 3. Net electric field of 0. We have them drawn the same length in both cases. Clearly one of those is incorrect, but the directions are correct. Yeah, go ahead, Ryan. 1. It would be 1. Yes, it would be 1. The answer is 1. How many people said that? Okay. Why would it be 1, Ryan?
Because it's further away from the greater charge.
Right. So this is closer to A than it is to B. Quite a bit closer, right? But the charge on A is smaller. So the fact that it's closer makes the field bigger. The fact that the charge is smaller makes the field smaller. Make sense? So if we're at point 1 and we're close to A, that gives me big field, but the small charge gives me small field, and they kind of cancel out. But if I go over here, look, not only am I close to B, which gives me a big field, B is actually a much bigger charge, which gives me an even bigger field than that caused by A. So they're both opposite directions, but only A gives me 0 net electric field. Two parallel plates, 1.5 centimeters apart, maintained at a potential difference of 250 volts. What's the electric force on an alpha particle here? Any ideas? Hey, let me write down my little Venn diagram. Green ones are valid in a, what do you call that? In a non-uniform electric field, right? Something like this. Blue ones are valid in a uniform electric field, where the electric field might look something like this. What do we got here? Uniform or non-uniform? What is it? Quinn, uniform or non-uniform in this question? Uniform. So it's the last two equations that are valid for us, right? What do you want to do? Want to find the force? Well, I'm probably going to use that middle equation then, right? F is equal to Q times E. But I don't know what E is, so I got to find that. Well, I'll use the last one, the producer equation, the uniform field producer equation. E is equal to delta V over delta D. So we're going to say it's 250 divided by the distance between the plates of 0.015 meters. And that gives us, I'm not sure what that gives us. But when we get it, we multiply it by the charge of the alpha particle, which is 3.2 times 10 to the minus 19, and then we end up with what force? Now let's find this out here. We're going to say 250. 250 divided by 0.015 gives me the electric field. Then let's multiply that by 3.2 times 10 to the minus 19. Gives me 5.3 times 10 to the minus 15. So my answer is A. Is that what you had said? Is that what you said? Yeah. Good. Oh, here's one. Here's a graph. That's a graph you've never seen before, isn't it? Uh-oh, what do we do with that? You know how to deal with that. It's a straight line graph, right? That's good. We got potential difference versus plate separation. Notice here, they're saying plate separation is D. This is an old question. They've changed the data sheet since this question came out. They used to call the plate separation D. Now they call the plate separation on the data sheet delta D. So really this should be a graph of delta V versus delta D. Okay? So don't get mixed up by that. If you saw that question on a diploma exam now, that's what it would say, delta V versus delta D. Okay, what are we looking for here? It says the rate of change of potential difference with respect to the plate separation. So in other words, what are we trying to find? The rate of change of potential difference with respect to plate separation. The slope. The rate of change of y as to x, that's the slope of the graph, right? Now, there's a couple things you can do here. How many people did like a rise over run thing? Which is, like, that's the standard, right? How many people did it on your calculator? Everybody take your calculator out right now. right now, I want to show you something. On your calculator, I would like you to hit not second function, just the stat button. Okay, stat button right here. Now you should see these options. Edit, calc, tests. You're going to stick with edit, and it's going to be option number 1, edit, edit. Got it? Click on it. Unless you've done something like this before, you should see a table like this that's empty. If it's not empty, then just delete each of the points. That's all. Now, if you had a bunch of data points like this, and we had just a trend line drawn, then what we would do is enter the x and y coordinates of each of those data points. Okay, but the beauty of this graph is that we don't. If we have data points, they're all right on the line. So when they're all right on the line, all you have to do is enter the first and the last, right? To get your rise over the run. Okay? If we got all of these points that are approximated by a trend line, then enter all of the points. But if you see a nice perfect straight line, then just enter 2 points, preferably the first point and the last point. My first point would be 0 and 0. Agree? What's my last point going to be? Well, it's kind of hard to tell actually on this one. Looks like it's 20. This would be 25. This looks like 21. Does that make sense? Is that what you guys used when you did rise over run? So 21 for the y and 10 for the x. Let's label that as 10 and 21. That make sense? Now remember, if we had all of these points in here, as opposed to just a straight line, then what we'd do is the same thing, except we would enter all of the points instead of just the 2 points, instead of just the first and the last. Okay? Now watch what I'm going to do. I'm going to hit stat again, but this time it's not going to be edit because I already edited those, right? No point in doing that again. So hit stat and then go over to calc. And then go down to option number 4, which is lin-reg, or linear regression, ax plus b. Go down to option 4, and depending upon your calculator, the version of your calculator, you may have to hit enter a couple of times, you may have to hit it up to 4 times. But just keep hitting enter until you get these numbers spitting out. It says y equals ax plus b, a is equal to 2.1, b is equal to 0. So in other words, the slope of this graph is 2.1, and the y-intercept is 0. Does that make sense? Does that make sense? Oh, you know what I missed? Oh, you know what I missed? I can't believe I did that. 10 to the minus 3 and the 10 to the minus 2, right? So what should I have done? Let's go stat edit. Let's change this. 0, 0 is fine. We got 10 times 10 to the minus 3. 10 times 10 to the minus 3, and then we've got 21 times 10 to the minus 2. Should have circled those in red so I wouldn't have had that issue, right? Now I go stat, calc, down to option 4, linear regression. Hit it 2 times, 3 times. If you have the TI-84 plus CE, then I think it's 4 times you have to hit it, but you'll figure that out. Here, what do we end up with here? The slope is not 2.1, the slope is 21, right? So we go to our question here, and my answer is D. Oh, look at, isn't this dirty here? Look at, if we hadn't caught our mistake with the exponents in the x and y axis there, 2.1, the answer's there. Dirty little people. Is that good? Number 7 says the proper SI. What does SI mean? Who are my people that when they write their answers, write 31,6? In other words, who are my people that take French? Okay. I don't even want to try to brutally pronounce this. SI stands for, it's French. It's French for international system. Système international. There, I did it. There, I did it. Is that okay? Système international. It's the metric system, right? What are the metric units for the slope of the line of this graph? Well, let's take a look at it's volts per meter, right? Y over X, volts per meter. There we go. Oops. I don't know what just happened there. Volts per meter, Y over X, right? You take the slope Y over X, the units are Y over X as well. The physical quantity that the slope represents is, oh, this one's good. The physical quantity that the slope represents. This is a good one. I don't know. What's the quantity? Like, what does the slope mean here? You guys know what to do with this, right? You've done this a few times now. Y equals mx plus b. What's on the y-axis? Delta v. M is the slope. Remember what I'm doing here? X is delta d. B, the y-intercept, was exactly 0. Now, what equation on your data sheet that has delta v and delta d in it? Rearrange this. Solve for delta d. You get delta v is equal to E times delta d. Oh, look. V disappears because it's in both. That shouldn't have a vector sign, by the way. Delta d appears in both. What am I left with? The slope of this graph is equal to the electric field strength. How many people did that analysis when they were doing this? Or tried to do that analysis? Hey, how many people just guessed electric field? Because it seemed logical. Okay? Do the analysis, because sometimes it might work out to be the inverse of the electric field or something like that, right? So the answer for that one is that field strength, yeah. Oh, that's a good question. This is the last one, I think, isn't it? Like this question. The electric field strength that's just sufficient to suspend a proton in an Earth's gravitational field. The electric field, we want to suspend it in the gravitational field. That means that this proton is sitting there. The electric force must be downwards. Sorry, the gravitational force is downwards. The electric force must be upwards. And the electric force must be equal and opposite to the gravitational force. We're never going to set the fields equal to each other. Fields can't be equal to fields, but forces can. And if it's suspended, the forces have to be balanced. Remember that. If anything's ever suspended, two forces have to balance. Might not be electric and gravity, but it's got to be something and something. Two forces have to balance. The electric force here is Q times E. The gravitational force is M times G. And we solve for E. It's mg over Q. So it's, proton is 1.67 times 10 to the minus 27 times 9.81. We'll just make it positive because it's absolute values here, magnitudes. What do we got here? Hey, Bruce, why don't you come on up and enter that for me? You want to do that? I won't make you do it. Just going to ask you a question here. 1.6 times 10 to the minus 27 times 9.81 divided by, what do I want to enter? 1.6 EE. EE. Okay? It's important, doesn't really matter so much on the top, but as a denominator, it's important to enter an exponent as an EE. Because then your calculator groups it with the base. 10 to the minus 19 gives me 9.81 times 10 to the minus 8. What did I do wrong there? Oh, that should have been 1.67, right? 1.67 times 10 to the minus 27 times 9.81 divided by 1.6 times 10 to the minus 19. 1.02 times 10 to the minus 7, D.